We continue to learn Chapter 6, Eigenvalues. Section 3, Diagonalization. Part 1, Diagonalizable Matrices. In this section, we consider the problem of factoring an n by n matrix A into a product of x times d times x inverse, where d is a diagonal matrix. We will give a necessary and sufficient condition for the existence of such a factorization and look at a number of examples. Okay. We first have this theorem, 6.3.1. If lambda 1, lambda 2 till lambda k are distinct eigenvalues of an n by n matrix A with corresponding eigenvectors x1, x2 till xk, then x1, x2 till xk are linearly independent. So if eigenvalues, they are distinct, they are different, then we can say their corresponding eigenvectors x1, x2 till xk are linearly independent. We prove this. Let R be the dimension of a span of x1, x2 till xk, and assume that R is smaller than k. So this implies that there are at most R linearly independent vectors in x1, x2 till xk. Okay, and assume that x1, x2 till xr are linearly independent without loss of generality. Since x1, x2 till xr plus 1 are linearly dependent, there exists scalars c1 till cr plus 1, not all zeros, such that c1 x1 plus till plus cr xr plus cr plus 1 times xr plus 1 equals 0. So this equation 1 holds. Note that cr plus 1 cannot be 0. If cr plus 1 equals 0, then x1 till xr, they are linearly dependent. So this is contradict to what we say, they are linearly independent. So cr plus 1 times xr plus 1 does not equal to 0, and hence c1 till cr can't all be 0. Multiplying both sides of 1 by a, we have c1 times a times x1 plus till plus cr times a times xr plus cr plus 1 times a times xr plus 1 equals 0. And because ax1 equals lambda 1 x1, because x1 is the eigenvector corresponding to the eigenvalue lambda 1, and also axr equals lambda r times xr, and axr plus 1 equals lambda r plus 1 times xr plus 1. Multiplying 1 by lambda r plus 1 and subtracting it from 2, we obtain c1 times lambda 1 minus lambda r plus 1 times x1 plus till plus cr times lambda r minus lambda r plus 1 times xr equals 0. Because lambda 1, lambda 2 till lambda r plus 1 are distinct eigenvalues, then x1 till xr becomes linearly dependent. So it is a contradiction to the assumption that R equals dimension of a span of x1 till xk is smaller than k. Hence R equals k and x1 till xk are linearly independent. So we prove this by contradiction. Now, definition. An n by n matrix A is said to be diagonalizable if there exists a non-singular matrix X and a diagonal matrix D such that X inverse times A times X equals this diagonal matrix. We say that X diagonalizes A. We have two remarks. First, if A is diagonalizable by X, the column vectors of X are eigenvectors of A, in fact, and the diagonal elements of D are the eigenvalues of A. The diagonalizing matrix X is not unique. You can find many different X. However, this D, if you consider, for example, the eigenvalues in the ascending or descending order, this is unique. Theorem 6.3.2. N by N matrix A is diagonalizable if and only if A has a linearly independent n linearly independent eigenvectors. Okay, we can prove this. Suppose that A has n linearly independent eigenvectors x1, x2 till xn. Let lambda I be the eigenvalue of A corresponding to xi for each I. Sum of the lambda i's may be equal. Let x be composed by those eigenvectors x1, x2 till xn. Then lambda j xj is the jth column vector of A times x. Therefore, A times x equals A times first column, A times second column, A times the last column. This from the partition matrix, right? The multiplication of partition matrix. Then because AX1 equals lambda 1 x1, AX2 equals lambda 2 x2, till the last one, AXN equals lambda n times xn. And this matrix we can write as this matrix X times this diagonal matrix composed by the eigenvalues lambda 1, lambda 2 till lambda n. So AX equals X times D. And because A has n linearly independent eigenvectors, so X is non-singular. Because it is non-singular, so you can pre-multiplying X inverse in both sides, you will get X inverse times A times X equals D. Okay. Conversely, suppose that A is diagonalizable. Then there exists a non-singular matrix X such that AX equals XD. If x1, x2 till xn are the column vectors of X, then A times xj just equals lambda j times xj. You just write each column, okay? Then lambda j here equals dj. Thus, for each j, lambda j is an eigenvalue of A, and xj does not equal to 0 is an eigenvector belonging to this eigenvalue lambda j. Since X is non-singular, A has n linearly independent eigenvectors. So till now, we have proved this theorem. N by N matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. Okay. Now, if A is diagonalizable, then the column vectors of the diagonalizing matrix X are eigenvectors of A. The diagonal elements of D are the corresponding eigenvalues of A. The diagonalizing matrix X is not unique. Reordering the columns of a given diagonalizing matrix X or multiplying them by non-zero scalars will produce a new diagonalizing matrix. Okay, if A is n by n and A has n distinct eigenvalues, then A has n linearly independent eigenvectors, and hence A is diagonalizable. So this is one simple case. If you find A has n distinct eigenvalues, because distinct eigenvalues corresponding to linearly independent eigenvectors, so A is diagonalizable. We have this one. And if the eigenvalues are not distinct, then A may be or may not be diagonalizable, depending on whether A has n linearly independent eigenvectors. So essentially, we should check whether A has n linearly independent eigenvectors. A has n linearly independent eigenvectors if the dimension of this null space of A minus lambda I, the eigenspace dimension of the eigenspace, equals the multiplicity of lambda for all repeated eigenvalues. If this holds, then A has n linearly independent eigenvectors. Then A is diagonalizable. Okay. If A is diagonalizable, then A can be factored into a product X times D times X inverse. Therefore, A power 2 equals XD X inverse times X times D times X inverse. We combine X inverse X together, and we will have this one equals X times D power 2 times X inverse. So diagonalizing this matrix A into a diagonal matrix, you will find it easy to compute power of A. So a power 2 equals this one, and in general, a power k equals x times d power k times x inverse. Where x inverse, you just write on the left, on the right side of this diagonal matrix, and d power k is still a diagonal matrix, which is a diagonal entries lambda 1 power k, lambda 2 power k till lambda n power k. Okay, that's why we like to diagonalize a matrix A into a diagonal matrix. So the computation for power A power k becomes much easier.